this lecture, I will discuss about loop unrolling. So, loop unrolling is the process of replicating the loop body multiple times and adjusting the termination code. So, for example, one example will take in which the constant will be added to each element of array. So, for that, what is the C code? For I is equal to 999, I get to then 0, get to then equal to 0 and minus minus x of I is equal to x of I plus C. So, it will unroll 4 times. So, what is the code? The loop body will be x of I is equal to x of I plus C, x of I minus 1 is equal to x of I minus 1 plus C, x of I minus 2 is equal to x of I minus 2 plus C, x of I minus 3 is equal to x of I minus 3 plus C. That means in one iteration we are accessing 4 elements of array. So as we are accessing 4 elements, that means the loop for termination code will be adjusted and it will be decremented by 4. That I is equal to I minus 4. Okay. Now I will show you regarding how we are doing through assembly language. Okay. So first of all, so what is the assembly language for this? So before writing the assembly language, you have to take some assumptions. So what are the assumptions? Let's say from an array whose starting index is 0, 1, 2 and up to you have contained the element 999. That means the index starts from 0 to 999. Okay. The assumption is, let's say R1 register. Register R1 contains the address of last element. Address of last element. Now, the size of each element is 8 byte. Size of each element is 8 byte. Another, let's say the index is minus 1, which is not exist. The address of this element is present in R2. So what R2 contains? R2 contains the address of minus 1 index. So why it is necessary? When you write, you can understand. Okay. And this constant value, let's say this constant present in F2 register. This constant present in the F2 register. Now I am writing the assembly language for this code. So first load So I will write the assembly language for this code. Load to F0. What I load? I will access this element. So how to access it? By accessing R1. That means load F0. So LD means it is a load double. Okay, and we were accessing a memory location. That memory location present in R1. So whatever present in that memory location, that will be loaded into F0. That means F0 contains what? Memory of R1 plus 0. Now, what is the second? Then we are adding this F0 to C. Okay, that means F2 R double F4 F0 F2. That means F4 contains what? F0 plus F2. Next, I want to store this result again into that location. Store double this result present in F4 into that memory location 0 of R1. Okay, so this for the single statement. For this single statement, you will write these three assembly languages. Now I will go for the decrementing I. So how I will decrement here? So that means here R1 is pointing to the last element. So what I will do so that what I will do in the R1 so that R1 will point to this. That means R1. Let's say R1 is here 2000. R1 is the 2000. Can you tell me what is the address of this element? Second last. So just minus 8 because this element contains 8 bytes. So just do minus 8. That means 1992. That means we are decrementing this R1 value by 8. So what is the instruction? DADDEY R1 is equal to R1 minus has 8, which means R1 is equal to R1 minus 8. So what is the meaning of this instruction? You are writing memory of R1 plus 0 this into, therefore we will write into this memory location. So here we are decrementing R1 value. That means R1 now is pointing to second last. Okay. Now you think about how we will do I greater than equal to 0. Is it the minus 1 index? That means when you are decrementing R1 value, is it R1 points to here? That means you will check this R1 to R2. Now we check this R1 to R2. So how we check? Branch not equal to R1, R2. If it is not equal to, then you have to go for the next iteration. Let's say loop. So loop is what? This location. Okay. So this is the assembly language for this C code. Okay, for the single iteration. Now we'll calculate stall. So how many stall in between this and total cycles per iteration. So our aim is to calculate total number of clock cycle per iteration. Okay. So how to minimize this thing? So to find out stall total number of clock cycle. So there is a assumption of the tables. So I will draw here. Now I have drawn the latency table in which it shows how many stall in between two instructions. If so, this column is the producer instruction. This is for the consumer instruction, and this is the latency. If this ALU instruction is producing one value and that value is used by the another ALU instruction, then there is 3 latency. If it is producer is the ALU and consumer is the store, then there is 2 latency. If producer is the load double and consumer is the ALU operation, then latency is 1. If it is load double producer and consumer is store double, then there is 0 latency. Okay. Now this side I have already written number of clock cycles per iteration. So how we are calculating? So this is our original instructions. Okay. So how many clock cycle it will take? 10 clock cycle. 10 clock cycle it will take. Now how this 10 comes? Okay. See. So this load operation, what? First clock cycle. Now it produces F0. Okay. And this F0 is used by the add instruction. That means it is a load instruction and it is a ALU operation. You see, load and ALU, there will be one stop. In between them, there is a one stop. So it is given in the table. So that's why load and add, in between this, there is a one stop. Okay. So load will perform at first clock cycle Stall will be at second clock cycle, R will perform at third clock cycle. Now, so this it produces F1 and this used with the store instruction. Just check it. Producer is ALU and consumer is the store. So how many store? 2 store. Okay. So you can see in between add and store. In between add and store there is how many store? 2 store. So store of so you can see so this store is a perform at 4th clock cycle. This store is at 5th clock cycle and the store will perform at 6th clock cycle. Now so as you can see here we are using R1, so there is no dependency. So DR instruction perform at the 7th clock cycle. Now see here we are producing R1 and here we are using R1. That's why there is a one store. Okay, and it is not given in the table. It is our previous information from the pipeline. So producing R1 and using R1. So stall is at 8th clock cycle and branch operation will perform at 9th clock cycle. And what about this stall? So as we know that in RISC, at ID stage we are getting to know whether it will jump to the target address or it will jump to the PC plus 4. So that means it takes extra one clock stall for to find that thing. So that's why stall is at 10th clock cycle. So what you can see to perform one iteration it takes what? 10 clock cycle. Okay. To perform one iteration it takes 10 clock cycle. So if you go for the 1000 iteration, so it will be go for the 10,000 clock cycle. Now our aim is to reduce that. Okay. So one method you can reduce by instruction reordering. The concept is the independent instruction we can place in between two dependent instruction. Already we have covered that thing. So one independent instruction we can place into the two dependent instruction. Now just see which one will be go to where. Okay. Your first instruction is load F0 R1. Okay, and this DR you can place here. Okay, so DR so that you can remove this term. This DR instruction I can place into here so that in between this independent instruction that stall is removed by the DR. Just say DADDUI R1 is equal to R1 minus 8. Then your R operation R double F4 F0 F2. Okay. Now, so in between this add and store there is 2 store, and again after the branch there is a 1 store. So what we can do? So BNE R1. So what you can do? So 1 store will remain there, and BNE R1 R2 loop. So this loop is the. Now in this store I can put the store instruction. Store double F4. Now when I am putting the 0 R1, it will give the wrong thing because R1 I already decremented to the second last element. Okay, so if you do this, then it will update here. So, but I want to place what at 999. So, what I will do? So, this offset value will be added by 8. Just understand why I am not writing 0 of R1. If you write 0 of R1, then what happens? Already, actually, what happens? Here we are performing the store, then we are decrementing R1. But what you are doing here? First we are decrementing the R1, then we are performing the store. Just swapping the two instructions. Okay. So because of that, already I have decremented R1. So that means R1 is pointing to the second last element now. So, but I want to update this value at the last element. So, for that case, I will add 8 to R1. Okay. Now see, in between load and R, that stall is removed. After the PNE, there is a stall that is removed. And add and SD, there is 2 stall. Between add and SD, there is 2 stall. So one stall is remained there, and one stall is used by the branch instruction. And in between DR and BNE, there is a one stall. You can see DR and BNE, there is a one stall. So this that is also removed. Okay. So if you calculate total number of clock cycles, just find out. So this will perform the first, this will perform second, this will be third, this will be fourth, fifth, sixth. So we can say that number of clock cycles for iteration is 6. Okay. As we are having 1000 element, so 1000 into 6, 6000 clock cycle. Now, okay, so total it will take this. Now question is, actually your x of I, that element x of I is equal to x of I plus c. So for this instruction there is only 3 assembly code. 3 assembly code. Okay, that means for iteration only we are getting 3, and there is another instruction which is the for the DR and branch. DR and branch. So that means our this instruction, this one and this one, this is performing x of I is equal to x of I plus c. Yes or no? So our aim is to reduce this number of clock cycle for iteration to what? 3. Can you achieve it? Can we achieve it? 3 clock cycle. Okay. We cannot achieve 3 clock cycle. Okay. But we can reach nearer to this by using loop unrolling concept. So already I have told you that for iteration we are getting 10 clock cycle initially. After the reordering we are getting 6 clock cycle. Now I will tell you how to improve this by using unrolling concept. So first understand the unrolling concept. See, unrolling concept, I am unrolling by 4 times. Okay, by 4 times. So when I am unrolling this load RSD, I have written 4 copies. Just see. I have written these 4 copies. Okay. Now see. So for accessing the last element, 0 of R1. Now I want to access the second last. This is for the second last element. So, but we are not updating the R1. Okay, R1 is still in the index address of the last element. So how to access the second last? If you can do R1 decrement by 8, that means minus 8 of R1. That will give what? The address R1 minus 8 means it will give the address of second last element, because each element takes 8 bytes. Okay, this is clear. For the third last, it is minus 16 R1. For the fourth last, it is minus 24 of R1. After that, so that means we are dropping here DR instruction, branch instruction. Dropping B branch DR, dropping branch DR. Now, this termination code I will write here. Okay. Now, R1 will be decremented by what? 32. Why? Because we have accessed last, second last, third last, fourth last. So that means this R1 initial point to this, now R1 will point to this. That means R1 will be decremented by what? Minus 32. Now, next is branch instruction, R1, R2, loop. We are taking the condition, whether we will jump to the loop or going to the sequential execution. Now, so how many clock cycles for this? So number of instruction already have written 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14. So 14 number of instruction. So how many stop? So for each set you can see there is 3 stop. How 3 step? Between load and add in the latency table already have shown you. Load and add takes 1 stop. In between add and SD there is 2 stop. So that means for each set we are getting 3 stop. So we have 4 copies. So 3, 3, 3, 3, 3. So 3 into 4, so 12. So 12 stop. Now DR, in between DR and BNE there is 1 stop. And after BNE there is 1 stop. So 12, 13, 14. So 14 number of stop. So you will get 28 clock cycle if you are copying 4 times. So for the one iteration, what will say? For one iteration, it will give 28 by 4, which is 7 clock cycle. Okay. Now this clock cycle is also very large than 3 clock cycles. So I want to improve again this. So by using the concept of unrolling plus reordering. So reorder means what? The independent instruction will put in between 2 dependent instructions. So what is the idea? So you can see all the load instruction. There is 4 load instruction. Make it one place. Next, add instruction. Make it one place. So what will happen? In between load and add, there is 1 stop. Between load and add, so that will be removed because in between this there is 3 instructions. Same for the store instruction. So between add and store there is 2 stop. So that is removed. Okay. Now, so again I am also solving. I am again removing this stop. So what I put? I put this D add instruction in between store instruction. Okay, so that I can remove this D add and BNE. That means D and BNE we have to put in the instruction so that there will be one gap. That gap will be used by the another instruction. Now, then store, then BNE, then store. Now you will see. So we have done 2 store operation here. Last and second last, we have stored it. When you are decrementing R1 is updated to this R1 minus 32. So if I will write here 0 or if I write what? Our instruction is what? 6 minus 16 of R1. Minus 16 of R1. Then minus 24 of R1. So in place of minus 16 R1, what I will write? Plus 16 R1. Why? Why I am writing here for this minus 16 R1, I am writing plus 16 R1 because your R1 value is already decremented. So that's why. So now R1 is pointing here. So I want to assess this one. So how will assess? If you add plus 16. Getting it? So that's why. For the third store instruction, it is 812 plus 16 R1. For the fourth store instruction, it will be plus 8. It will be plus 8. Okay. Now you can see all the stores are removed. Now just calculate how many clock cycle. Total clock cycle is 40. So per iteration, clock cycle per iteration is to give 14 by 4. Which is 3.5. 3.5.